All right, so I think we are ready for the last talk of this short course by Camille Laurent-GENGOUX. So please go ahead.
Where are we? I'm going to recapitulate what we have seen so far. I think it's good. So today, I will first just do a quick revision of whatever has been said. Then I will give more hidden structures behind a singular foliation, and for each one of these hidden structures, I will ask open questions, some of which are mine, some of which are around in the singular foliation community from quite some time. So first of all, where are we? So let me recapitulate the whole story. So we had this definition that I call the consensus definition. Of course, consensus are there to be rejected, of singular foliations that had three items, alpha, beta, and the gamma, which were respectively, it has to be a safety module of vector fields, which is alpha, a safety module, beta involutive, and gamma locally finitely generated. Right? But I showed the first day that there is an error in the sense that it induces what I called a partition manifold. So just a partition manifold. So just a partition of the base manifold into immersed, locally closed sub-manifolds. But more than that, it's a smooth one, which means that if I'm at this point, if I know the leaf through this point is a straight line, I take this vector, and I'm sure that I have a vector field tangent to all leaves that go through this as a vector. So what we showed is that this induces this. By the way, here is the first open question, but it's maybe just open because of my ignorance. Maybe it's even in the article by Sylvain Lavaux. Is this onto? I don't know, in fact. I would say no, but I could not figure out a counter example. Okay, first open question. But it could have been solved in the 1970s. Okay? So maybe just the effect of ignorance. Okay. This was Tuesday. Okay. And Wednesday, I started to look at the hidden structures, and I said, I don't know what kind of arrow I should say for hidden structures, like maybe like this, like a snake. I don't know. And well, I had this point of view that is debatable, by the way, that the most fundamental hidden structures, because there are many, although they are all equivalent in some sense, which is behind is an almost the algebraic on some anchored bundle. Too small. A with anchor rho. So I want, sometimes it's good just to repeat things because I didn't say everything. I want to say another time, but in slightly different ways, exactly how you get this almost algebraic, because Wednesday I forgot to say something. How does it work? So, proof of this. How does it work? You have an anchored bundle over F. Okay? Anchored bundle over F. So what does that mean by definition? Do you remember? Yes?
Row of the sections of the bundle.
Exactly. I take all sections of A, I apply rho to get vector fields. I want to get F. Okay. So near any point, there exists a trivialization. So trivialization, maybe it's two-differential geometry award, means I have local sections that form a basis at every point of A. Trivialization E1, ER, such that rho of EI equal xi are generators of F. When I say generators of F, I mean generators as symmetry of M a module, right? Okay, that's anchored bundle. How do I define the almost algebraic bracket? I say, oh, F is a foliation. So for all indices I on j, xi, xj, it's in F. So there exist functions Cij, these are, do people online can see if I write that up blackboard, but who's online? Yes, okay. Symmetry of M, such that we have this. And without any loss of generality, I explained that you could assume Cji k is minus Cij k. Okay? So how are we going to define the bracket of? Okay? That's precisely follows from the axioms of singular foliation. It's closed under bracket. Okay? So now we define a bracket. Now on sections of A, how do we do? Like EI, EJ equals sum from K equals 1 to R of Cij K EK. Okay? But that's not enough. So far, the anchor is just defined on R element, the trivialization. And the brackets are only defined on, well, on two elements of the trivialization. So it's not defined on the whole as a sections, but that's fine. We extend anchor by linearity. Okay, and you extend bracket. Now that you have the anchor defined everywhere, linearity of a function. Okay, you extend bracket using the Leibniz rule. Okay. Good. So now sections of A comes equipped with an anchor rho and the bracket. But wait, the bracket is only defined on some open subset. It's not defined everywhere. Okay? What does this guy satisfy? Is it only algebraic? In general, no. Here, if you compute the Jacobiator, you get 0. But here, if you compute the Jacobiator, you get weird expressions with Cij A, Ca, Kb plus derivative of that equals 0. In fact, what you would get is a relation between the generators, so it comes back to that later. But you get an almost structure in the sense that Jacobi is not true, but the anchor map is a morphism. We have rho of AB equals rho of A, rho of B. Okay? But in fact, it's an argument due to Marco Zomon, should give credit. That's only locally. And something very surprising if you know Poisson structure, if you know Lie algebroid. How do you get it globally? You just glue using partition of a unity. It's very strange. No way you can glue Poisson structure using partition of a unity. Jacobi is not kept. There is no way you can glue algebraics using partition of a unity. Jacobi is not kept because Jacobi is a quadratic equation. But almost, it's linear in the bracket. Just use partition of your unity. Okay? You just glue them by partition. You glue them just by partition of unity. You have your local brackets. This guy is still an almost bracket. Okay? This is surprising. Absolutely nothing like this, again, if you work in the Poisson world, if you work in the Lie algebroid world. Okay, to repeat, and this argument I forgot to give yesterday. Okay, so where are we? Okay, we have our almost Lie algebroid on every anchored bundle. Let's assume there is a global anchored bundle. It just means the singular foliation is globally finitely generated. Reasonable assumption. I explain that out of that, well, so yeah, that's a bit embarrassing. I have to lower. Maybe I do. No, I cannot. Yeah, like this. Well, I explained that with this, you can prove that. You use classical Lie algebroid tricks. You see section of Lie algebroid as a linear vector field. You integrate, and it gives you the symmetries of F that are going to prove you that the leaves exist. Okay, it's good for proof. Okay, there are other elementary proofs. I mean, you don't need it. It's just a point of view. Now, out of that, many things you can get. You can get at Androidakis de Born-Skandal is called the isotropy, the algebra. So at each point, you give yourself a point. At each point, you have a Lie algebra. I re-explain the notation GMF. I don't know how to say that there is a matfrak behind this G. I don't know. Maybe we have G like this. Okay. I always matfrak, I know. At least in Androidakis Skandal is when they invented it. I think there is a matfrak. Oh, so GF of M, sorry. No, GM of F. Anyway, there's a Lie algebra at every point. Just repeat in one word how it works. You take, at that point, you take the kernel of your almost Lie algebroid, and you divide by the strong kernel. So you divide by elements in AM, through which there are sections which are killed by rho at every point in the neighborhood. Or you can see it as being, and it is the original construction, as being elements in F that vanish at M divided by F times all function vanishing at M, this one being a subset of this one. Good. Well, you can do something slightly more general. You fix not a point, but a leaf. You get something, I've been now well studied by Androidakis and Zambon in particular. You get the holonomy, the algebroid. Well, it's when you fix not only point, but a leaf. If you want, it's a way along the leaf to glue all these isotropy Lie algebras into a transitive Lie algebroid. Maybe I should say a little bit more about that. Well, okay, I see in some eyes. Well, it's a Lie algebroid, which is transitive over L. It is over L, just over the leaf. I call F the leaf. It's over L. It's transitive. They give it a name. Oh, sorry, it's beginning to be messed up. So Lie algebroid, denoted by AL. I just say sections of AL. It's all of F divided by ILF. So all elements of F divided by all elements of F times functions which vanish on L. This seems to be defined over the whole of M, that because I divide by ILM, in some sense you can ignore whatever is not L, it becomes concentrated on L, and you can take just the algebroid over L. Okay. Something else I'm going to recall that out of the almost Lie algebroid, you also get a bi-submersion. I'm going to recall the definition. Called the chart bi-submersion, the fundamental bi-submersion. I will just recall how is it constructed when A is a trivial bundle. Assume A is a trivial bundle. Again, too small, sorry. With generators E1, ER. Okay. Then I just map A to M by two different ways. Here I just take the projection, easy. And from here to here, I map lambda 1, lambda R, M. So you see M is a base point in M, lambda 1, lambda R are the coordinates in this trivial bundle. I map it to the time one flow of the sum of the lambda I xi of M. The theorem is that this is a bi-submersion. I will recall soon what bi-submersions are in the neighborhood of the zero section. It's a hard theorem. Actually, it's the same. I should add an arrow like this. You have to prove that singular foliations are flows of themselves to prove it's a bi-submersion. It's kind of beginning to be kind of messed up, no? But it's where we are. I'm sorry. Okay. Now, out of bi-submersion, you can construct a groupoid I'm going to say more about, which is Androidakis Scandalis holonomy, holonomy groupoid. That's exactly where we were. And I'm going to say more about this. I'll mention that in fact there is a direct path like this by Garmendia, Villatoro, and I have also a version of this by Lavaux and Strobel. So there is a direct way to go from the almost to AS holonomy groupoid. In fact, yeah, I should explain it because I think for people who know the Severa Weinstein groupoid that Kreinig and Fernandes used to integrate Poisson structure is very unnatural. Basically, you mimic the construction being A paths, being up to A homotopes, kind of mimic it for almost Lie algebroid, and you will get not the AS holonomy groupoid, but it's universal like cover, but you can make some more diversions and you get holonomy groupoid. Is it clear? Is there any question? Oh yes, of course. There are more errors. Okay, I'm going to say more. It's even, yeah. I would describe the one from holonomy groupoid to isotropy Lie algebra. It's even easier. A groupoid, you restrict at a point. You get isotropy, you get a group. In that case, it's a Lie group. Why it's Lie algebra, isotropy Lie algebra. Now, Claire de Boer proved But if you take this groupoid, well, the orbits of this groupoid are precisely the leaves of the singular foliation. So take a leaf, restrict your groupoid to that leaf. This groupoid is absolutely not smooth. But if you restrict to the leaf, it is smooth. So it's a Lie groupoid. And if you take its algebraic, you get the holonomy Lie algebraic. So in some sense, Androidakis Kondalis holonomy groupoid is just you take all the holonomy Lie algebraic and you integrate them. But if you do that, you are losing information. You're losing part of the topology, and you don't know which one of the cover you have to take. More questions? This one? Well, actually, I could replace it like by phi lambda 1 of x1, phi lambda r of xr. And then it depends on order. But if I define like this, it doesn't depend on order. But this one would do the job also. It would also be a bi-submersion. You see, I follow first x1 during time lambda 1, then x2, then x3, then x4 during time lambda 2, lambda 3, lambda 4. Actually, that's an interesting example while Oscar is working on it. Because when you have a singular foliation generated by vector fields which are, let's say a big word, algebraically integrable. I mean, just means you can compute the solution by hand. Sometimes differential equation, you can tell at the end that the solution is the cosine of exponential t, right? Sometimes it's just no way. So assume you can, singular foliation is generated by vector fields that correspond to differential equation that you can solve by hand. The fact that this is a bi-submersion means there is a bi-submersion you can compute by hand. Okay. Sorry if it's not. Yeah. Good. So I come back a little bit to. I wanted to recapitulate. In fact, I didn't realize my class was such a mess. But okay. That's how it is. Okay. Yeah. So what I'm going to explain now, I just recall definition of this weird object that I think is very important, which is called bi-submersion, and try to ask question, is it groupoid-like, yes or no? Let's recall the definition. We take a singular foliation F on a manifold M. A bi-submersion, it's a triple X, S, T, oh, X here. ST, sorry, yeah, such that source and target are submersions, S and T called source and target. And, okay, maybe I should draw in the same time. So you have X. S and T. And what you want is that if you take the pullback of F by S and the pullback of S by T, you want those to be the same singular of a foliation. But that's not enough. You also want that singular of a foliation to be made of all vector fields of the form X plus Y, X S vertical, Y T over vertical. Have three conditions, like S minus 1 of F is T minus 1 of F, three identities, well, two, I don't know. And it's K of TS, K of TT. Okay? So again, if your bi-submersion is just a Lie groupoid, what these three things are is just to take all right invariant vector fields, all left invariant vector fields, look at the module they generate, and you get this thing. It's not easy, by the way. You have to prove. Okay. So now it's more like hand waving for a few minutes because I have no time to enter into detail. I can agree this definition is very confusing. I was very confused first because I think my confusion was, is it kind of Lie groupoids? And I'm going to try to explain you that it is like a groupoid, a Lie groupoid, but it is not like a Lie groupoid. I'm going to be the pessimistic and optimistic. I don't know which one is which one, by the way, at the same time. Okay. So what is Lie groupoid like? There is a source, there is S, there is T. That's very much like Lie groupoid. A target, a source. Fine. That's a yes say, I would say. Oh, a unit are perfectly defined. Units are maps from M to X, which are left inverse or right inverse of T and S. I mean, there are sections of both S and T. So there is source, there is target, there is a unit. Okay. Looks like groupoid, but it's not like groupoid. There is no product and there is no inverse. I say there is inverse. There is a unit, there is source, there is target, there is no inverse, there is no product. And then the yes sayer will say, yes, there is an inverse, yes, there is a product. It's just this. Maybe I should erase the whole blackboard instead of leaving half of the proofs. What is the inverse of this by a submersion? It's this by a submersion. I just took S and T and I flipped them. Okay. What is product? Well, I have a bi-submersion like this. I have another one like this. I'll define their product to be the fiberette product over M. We have an inverse, we have a product. Okay, but the naysayer will say, come on, it's not an inner rule. The inverse should map the groupoid to itself. Here I'm mapping a bi-submersion to another bi-submersion, and the product takes two bi-submersions, so make it another bi-submersions. Doesn't make any sense. Okay, but then the yes sayer will say, well, it's okay. I will construct an atlas out of the fundamental groupoid. How does it work? It works like this. I told you if I have an anchored bundle, I just call A. In fact, it's a neighborhood of zero section is in A, which is a submersion. And then I consider this, where, I don't know, make a symbol here. I take the disjoint union n times, disjoint union for all n in M, where this symbol here, I mean, it can be -1, or it can be just empty. Just don't write anything. Okay? So I take A, I product or A-1, I take the product with A or A-1, take the product with A or A-1, blah, blah, blah. Okay, and again, I wrote A, but it's a neighborhood of zero section in general. Well, with this, you have a product and you have an inverse. I mean, the inverse is just to write everything in different order and you change these spirals into the and have a product. Okay. But then the naysayer will say, okay, but it's still not a groupoid structure. It's kind of associative. That's okay. But the inverse is not an inverse, right? All right. But the yes sayer will say, okay, there is no inverse, but it's not like groupoid, but there is a notion of Morita equivalence. How does it work? So it's not at all the way introduced in Requisens Scandalis, but I will say two bi-submersions. I say they are equivalent if there is a third one and two arrows and two arrows and two red arrows like this. That makes everything commuting. This looks very much like Morita equivalence, if you know Morita equivalence. All right. And then the naysayer will say, okay, but I looked at Androidakis Scandalis article, and it's not at all the way it works. What is going on is that, in fact, so first thing, very surprising, if there is a map from X to Y, in fact, it's an equivalence. So all maps are, in fact, equivalences. It was an onto map. In fact, what equivalence means has to do with bisections. So I will explain what bisections are. That's something the yes sayer can say. You know, if you have a Lie groupoid, bisections are a nice object because they give you Lie algebraic automorphism of the base. Same thing here. So if you have a bisection, I record a bisection here, it's a sub-manifold, the restrictions of which of S and T are diffeomorphism. So if you have a bisection, you have an induced map here. So the bisection I call sigma, induced map I call sigma underline. Okay. If you have a bisection in a Bi-submersions, you have a map from M to M, a diffeomorphism, take S minus 1 then T, and a theorem, exactly like for Lie groupoids. I mean, for Lie groupoids, if you have a bisection, it induces a map from M to M, which is in fact the base map of a Lie algebraic isomorphism from A to A. Here, what do you think we get? If you have a bisection, the induced map is the symmetry of the foliation. It maps F to F. Okay? And in fact, I'm just saying it with hands. What this word definition of equivalence means is that for every point X here, or for every Y here, there is a Y here, or there is a X here, such that there are bisections through X and Y that induce the same diffeomorphism on the base. So X and Y are equivalent. If for every point here, I have a point here, or every point here, I have a point here. And two bisections through this point, local bisections, small bisections, that induce the same germ of symmetries of singular foliation downstairs. That's very not like Lie groupoids. That's very different. Okay. So it's not at all. Okay, so we have bisections induced as symmetries. That's fine. But it's not like the same. No, yes?
Just one fraction here.
Yes?
Is there an infinity groupoid now?
Is it?
Is there an infinity groupoid there somehow?
Probably. Good point. Well, it's associative, kind of. Probably. Maybe. I don't know. I would say it's not the idea. But I can explain later why. Okay. So, okay. But now, what you are going to do is to take this atlas. Okay, and you identify 2 points in 2 different of these elements if they have neighborhood which are equivalent. Okay, which means if they kind of induce the same germ of diffeomorphism on the base. If you know the holonomy groupoid of a regular foliation, it's very unnatural. And the theorem is that if you do that, you get a groupoid. So you take the fundamental atlas, you divide by an equivalence relation, which is this equivalence relation applied to itself. So identify 2 points if they have neighborhoods where I Bi-submersions they are equivalent, and you get a decent groupoid. Like there is a product which is an inner rule, an inverse which is an inner rule, a source, a target, a unit. You have everything. You have associativity. You have gamma 1, gamma 2 minus 1 is gamma 2 minus 1. Gamma 2 minus 1, gamma 1 on everything. So you get a groupoid. Now, it's a little bit of work to check it, of course, but you can check this. That's AS holonomy groupoid. And, well, all that, the questions you asked me, it's a little bit of work to check that it's actually that. Is there any question? Because I'm going to ask a question now to the audience. It's okay? Construction? Yeah, it's a bit It's very strange, you see? It seems almost like what we are used to in Poisson geometry, almost. But at each step, it's a little bit different. So the logic is kind of similar, but still different. Oh, I forgot the last line, but I already answered this question, which was, okay, so the quotient is groupoid, but it's not Lie, the naysayer would say. But then you can use the Claire de Boer and say, oh, on each leaf it is Lie, but not on the transversal. That's correct. On the transversal, it's a topological groupoid with a horrible topology, like not separated, not just the worst topology you can think of. Okay, I got everyone lost, or? Okay, so here's a question. I mean, I have no idea what the answer is. There are many results in Poisson geometry literature, in groupoid literature, in algebraic literature. I cited many names of linearization when the isotropy algebra is of compact type, or when the groupoid is of compact type. Around the point, or like the lot of you marked recently, around the leaf, right? So I have two questions in this spirit. Assume the AS holonomy groupoid is proper. And this makes sense, proper. This has a topology. Probably equivalent to say that you have a Bi-submersions, which is kind of proper.
It's not alpha.
Sorry?
This groupoid is not alpha.
No, no.
For non-alpha topological spaces, there are very different notions of properties.
I don't know. I would say just assume each holonomy in the algebroid is proper. This makes sense. Or assume the manifold is compact, and this is compact.
Or maybe you require alpha.
Right. Right. Okay. So does this imply the singular foliation you started from is linearizable? I mean, we know for groupoid is proper. We know, Soon, Kreinig, Fernandes, many authors proved and reproved with nicer proofs that in that case, in fact, the groupoid is just a compact Lie group like SON or SUN acting on a vector space by a Riemannian transformation. So could it be the same for singular foliations, like properness, whatever it means, part of the question, if you want, of the holonomy groupoid implies linearizability? Or is it even more elementary on that? Like, if you have a leaf which is reduced to a point, is the isotropy the algebras of compact type, like it is SON or SUN, is it enough to guarantee that locally, in fact, you just have SON or SUN acting on the vector space? I really have no clue. I mean, I have no counter-example at least, and so on. Dominique Cerveau in 1976 proved, the article is written in French, but that we reproved it with Leonid Rivkin recently, proved that if Gm of f is a semi-simple Lie algebra, then it's formally linearizable. But it is at the formal level. All linearization results are easy at the formal level because H2 of a semi-simple Lie algebra in whatever is finite dimensional is 0. Okay, so a formal linearization, you just need this to be semi-simple and it works. It is just a formal. Locally, I don't know. Okay, so much time do I have left? 15 minutes? Okay. So, okay, and I jump to a totally different type of question. Well, maybe not totally different, which has been around for quite some time. So it's Androidakis and Zambon where the first question appeared in a printed way the first time. Well, I said that among examples of singular foliation, there's an important one which are imaged through the anchor map of a Lie algebroid. Question, around the point, or for globally finitely generated singular foliation, is it always the image through the anchor map of a Lie algebroid? See? Like, the one I have constructed is not Lie. It's not Lie because if I compute Jacobi, like this, I compute Jacobi, in general, we don't get zero. We get some relation, k equals 1 to r, with big thing here with c, I, j, a, c, a, k. Oh, k is not good. I call it it's A, B, C, D, A, K, I, D, plus circular permutation on I, J, K. And here I have another term, which is minus, by the way, xk of C, I, J, B. I mean, we don't get zero, we get some expression like this. Okay? So this question is, can I choose these coefficients? They are not unique. You may have a relation between your generators. Can we choose coefficients so that these guys are equal to the zero? Okay? And if it does not work for that anchored bundle, maybe we just add an unnecessary vector bundle, like you add generators that are of no use, that would allow you to gain the Jacobi identity, maybe. Right? And I already solved it yesterday, I say it again. The pure scandal is that you just take vector fields on R2 that vanish quadratically at 0. Can you find a Lie algebroid where the image is this? That's very strange, it's so hard, or maybe I don't know. Like, why is it not easy? But maybe there is, maybe we just didn't have the right point of view. But why is it so hard to find or to prove it cannot exist a Lie algebroid of a finite rank on R2? I mean, it's not a complicated space, it's R2, but the image of the anchor map is all vector fields vanishing with their derivative at 0. Why? Infinite dimensional it exists, always. But finite dimensional, no clue. So my personal point of view on that is that I would say probably not. I think the answer is no. I think sometimes it's not a good question. And no, I'm afraid I'll be like stamp collectors, as I told, who tell about their favorite collections that nobody is interested in them. To explore this question, I will explain the thesis of Sylvain Lavaux, the one that was, I had a skull because I said, okay, it's weird structures. Well, behind the singular foliation, you have more geometrical structure than just an anchored bundle. Let me explain. Okay, I have F, and the anchored bundle was a vector bundle, A, so that if I apply rho to sections of A, I get F. Let's continue the game. So, sections of A is the kernel of this map now. Against the symmetry of M a module. Assume you play in holomorphic or real analytic. Submodule, finitely generated. What does it mean, finitely generated? It means I have another vector bundle B and a morphism of vector bundle from B to A that induces a map from sections of B to sections of A that make this complex exact. Okay? Then I can continue. Okay, here I have a map from sections of B to sections of A. Its kernel is the CFT of M module. So we can find a vector bundle C and blah, blah, blah. Okay? We call it a geometric resolution. Okay, with Lavaux and Strobel. And Well, we have been able to prove that for most singular foliation, this exists. Now, of course, most, I think the referee will criticize. So a more exact statement we found out is if you have a singular foliation on a relatively compact open as a subset, such that near each point, it has generators which are real analytic. Okay? But I even don't want the way we change of chart to be real analytic. It's a bit strange. It has to be locally real analytic, but the change of chart may be not compatible with this real analytic structure, we don't care. Then there is a geometric resolution of a finite length. Okay, technical resolution, I mean, most examples are like that. Okay? Unless you really want not to be. How do we prove it? I just say through the keywords. Near a point in real analytic, there's a CZG. To say that real analytic resolution implies it's still a smooth resolution, Tougeron, Malgrange, flatness of smooth, germs of smooth functions over germs of real analytic functions. So near a point, we get a resolution. No one has to glue resolutions. Just hard computation, partition of units and blah, blah, and you glue them. Okay? So I would say a CZG, Tougeron, Malgrange, some stupid trick to glue. And you get it. Okay. Now, well, on this guy, there is an almost algebraic structure. So now I will justify this skull there. So if a theorem on this wall, guys, there, you have what is called a Lie infinity structure. Okay? So, there's a long result behind that. We have to give credit so to Chen Chang in particular, who was having the first one, and we knew it when we did it. With Ralph Meyer, discussed already this idea that take a foliation, you take a resolution, there has to be a infinity algebraic structure on that thing. Also, after we published the article, this we knew when we did it. After the article was published, we get notes by Voronov and Koudaverdian, who also had discussed it like 20 years ago, a very long time ago. And there was also Johannes Utzschmann, who has a way of saying it. It's a bit different, but kind of. It's more or less that also. But it's not just existence. It's also, it's LFT algebra, it's universal in some category, which means in particular that as any universal object, it's unique. But we work with Lie infinity. Lie infinity is never unique. The best you can have is unique up to homotopy equivalence. Okay? We have an infinity algebra structure here. The infinity algebraic structure, what it means is that if you compute Jacobi, you don't get 0, but you have a free Harry bracket that gives a homotopy with 0. Okay, with signs here. Plus the free Harry bracket itself satisfies kind of higher Jacobi up to homotopy, and blah blah goes to up to infinity. You have a 4 Harry bracket, a 5 Harry bracket, and so on. Okay, so. All right, we have a structure, but what was its use? Well, I'll give, so, oh, sorry. Come back. Well, okay. We have a complex here, but this complex, I'm going to erase, my students hate that. It comes, I define it using the sections, but in fact, it's a complex of vector bundles like this. Complex of vector bundles, I can restrict them to a point. We still get a complex. Okay? Do you think this complex is still exact? The previous one, the section was exact, right? But when you restrict to a point, if it's a regular point of the foliation, still exact. Singular points are precisely those for which it is not exact, so it has cohomology. The first cohomology is the isotropy Lie algebra. It's kernel by strong kernel, because at each time it's kernel by strong kernel, kernel by strong kernel, kernel by strong kernel. If you like algebra, you can see that this cohomology is stored on FC. Don't worry if it was not understandable, mistake it. Okay? So this LFT algebroid structure gives an LFT algebra structure on that cohomology. Now, general things. When you have an LFT algebra structure, on the level of cohomology, you have a differential graded Lie algebra, and the free Harry bracket gives you a Chevalley-Heidelberg class in this differential graded Lie algebra. Of a theorem, if this class is not zero, that we have with, again, the thesis of Sylvain Lavaux, if this class is not zero, then there is no way you can, why have I erased? Anyway, there is no way you can choose on that anchored bundle, but you can undo that anchored bundle with a Lie algebroid structure. It is very strange, like, shouldn't have erased that. I showed you that existence of a Lie algebroid, it's some weird relation in the choice of the generators. Why is it that you need to go through Lie infinity algebra to be able to answer to the simple question, no, there is no choice of this Cijk, so that this weird expression I wrote can be zero. You see, it seems disproportionate in the abstractization, but so far the only proof we know. Also, I think it replies the questions of existence of the Lie algebroid in a way that, okay, maybe there is one, there is not. But even if there is, it's kind of arbitrary. The object which is well defined is the homotopy equivalent classes of this universal Lie-T algebroid, what we call universal Lie-T algebroid, or universal Q manifolds. How much time do I have left? 3 minutes? Oh, okay.
Can I ask you a question about what you just said?
If I still have 3 minutes after, yes.
I mean, we start with the 10 to
Okay.
12, so,
Mhm.
Isn't there a homotopy invariant that will decide this question? Because instead of fixing the bundle, you are
Yes.
interested in
Right.
this L-infinity algebra up to homotopy. Invariant that will tell you that it's not homotopy equivalent to a real.
So you are getting right to the point where it hurts. And by the way, Karen Deb Singh made just precisely some progresses on that. So the problem is, if it's LFT algebra, assume it was just, it is called a string algebra. So you have a semi-simple algebra here, R here, and the free Harry bracket is a Cartan free form. I mean, that's well known to be a stringly algebra. If we had that, problem solved. Why? Because this Lie-T algebra is never homotopy equivalent to a differential graded Lie algebra of finite dimension. So this would solve the problem. Unfortunately, because of servo-linearization theorem, both problems are linked. In fact, the semi-simple part, in fact, this can never, this kind of things will never happen. Because if here I have a semi-simple, the foliation is linearizable and there is no need of free Harry bracket. So in fact, these classes of obstructions, I think they are always what is called effaçable, which means erasable, I don't know. Which means on the semi-simple part of the Lie algebra you have first, they are zero because of linearization. So they just come from the nilpotent part, and then by enlarging them, you can get rid of them. Now, Singh has an example where, in fact, seems to be more complicated, like, but yeah, so to answer your question, it was an initial dream, right? We get an nifty algebra which is not homotypically equivalent to infinite dimensional, and the answer is no. But unfortunately, there are always, I think, a nifty equivalent to finite dimensional differential graded Lie algebras. So you can't really get definitive no out of that. That's why it's a hard question, I think. Okay, so what are the various uses of this nifty algebraic structure? Well, when you have deformations, yeah, you want deformations to be classified. It's a general thing in Poisson geometry, in regular foliation, in complex structure, and so on. You want them to be classified. It has nothing to do with what I'm drawing, by the way. To be classified by a differential Laurent-Cartan equation, some differential graded Lie algebra. Okay, and with Lavaux, prove that if you want deformations of singular foliation, in the formal way, are classified by some DGLA of vector field of nifty algebroid. Just think of this as a horrible word. I'm not going to explain what it is, but it makes sense. Okay, so formally, we know what classifies it, but it's just a formal thing. Deformations, you would like to get strong rigidity of theorems. And I can explain you an easy example. Concentric circle. Is it stable? No. You can deform them. You can deform the circle into spirals. Yeah. See, if I take the foliation of concentric circle, I can deform it. I just choose a spiral. I make the spiral turn like this. And that's a deformation of this guy. Okay, I didn't say everything, so more than that, we keep the symmetry of M structure constant. We want as a module F to be always the same, but we deform the way we put this module into vector fields. Otherwise, you can just add all vector fields. That was a deformation. But you cannot do that with spheres. Think concentric spheres around the point. You cannot make a spiral out of that, like spiralic sphere doesn't exist. So this one seems to be rigid. This one seems to be not rigid. And you will see what my next question is. Take Poisson structures well known to be rigid, like SON star, SUN star. Yeah. Okay, it's like SO3 acting on R3. That's a rigid Poisson structure. It's a rigid group action, SO3 acting on F3. Many ways it is something rigid. But are these concentric spheres still rigid in the sense of singular foliation? You see, it's just a slight generalization. But concentric spheres, you see them as an action of SO3 on R3, it's rigid. You see them as symplectically, so the Poisson structure on the dual of SO3, it's rigid. Is it rigid still as a singular of a foliation? Of a formally, yes. But, yeah. So, very surprisingly, there are other questions that it's funny because you don't see singular foliation, you don't see higher structures, nifty algebraic structure either. The case of Ruben Louis, who did the exercise class yesterday, using this kind of structure, he was able to answer this kind of question. We take an affine variety and assume you have a Lie algebra that acts, but only acts on the affine variety. Can you extend the action to the ambient space into a Lie algebra action? If it's R, yes. If it's R2, already we don't know. And in fact, what he did is to say, oh, that's a story of symmetries of the singular foliation of vector fields vanishing on the affine variety. And if you can extend, it means that some parts of this Friari bracket can be killed and you get obstructions and blah, blah, blah. Again, it's funny because when you look at the problem, take an affine variety, take the algebra acting on it, like R2 with trivial product. Can we extend it to the ambient space? Doesn't seem to be nor singular foliation nor unity algebraic, but it appears somehow. How many do I have? One?
Yeah, now we are getting we have 1 minute.
Okay. Well, for regular foliation, there's an important class called the Molino class or Atiyah class or the Molino-Atiyah class. I'm not going to explain what it is. It's something that you have the dot connection. And it's an extension of the dot connection in the normal direction. And it's the vanishing, what it means. What it means is that if I take the first return map, it's a linearizable map. So it's just a class that obstructs the possibility of linearizing all the first return maps. Only defined for regular foliation. Simple question. How do we define it for singular foliation? What is its geometric meaning? Last question. Well, I start with the last, but I do the anti-last. Last questions. What are the good cohomologies of singular foliation? So there are various attempts, like with theologies, like Miyamoto in Toronto, but using the definition of smooth partition manifolds. You have definitions using this entity algebraic because there are Q manifolds. Q manifolds have cohomologies. You have other definitions. I don't know what are the relevant cohomologies for singular foliation. That's a vague question. This question I will finish on that. That's quite interesting. Joint work with Leonid Rivkin. And we did some things, we did everything. If you have a regular foliation, if you have a leaf which is simply connected, then the regular foliation is locally trivial. For singular foliation, it's not true. Things vector fields tangent to the zero section in TS2. That's clearly not trivial, otherwise TS2 would be trivial, so no way. So obviously you have more than pi1 of the leaf, you have pi2 of the leaf, pi3 of the leaf. I mean, you always have quite a lot of structure that can play a role. I mean, all the pi n of the leaf obviously play a role, and with Leonid Rivkin, we at least we found a map from pi n of the leaf to pi n minus 1 of universal leaf T algebraic. Right. We started this question. But we also have very strange results. But I just cite one because it's very surprising. Assume you have a singular foliation that has a leaf L, which is simply connected. And assume the transverse singular foliation is made of vector fields. So the problem is what? You have a leaf and you have your transverse structure. Okay? And you want to be able to construct a neighborhood of the leaf out of that leaf L, that transverse structure, and something else. But we were able to prove that if this transverse structure is made of vector fields that vanish quadratically at the origin, then formally the singular foliation is trivial, which is absolutely not true for the algebraic, absolutely not true in Poisson geometry either. That is true. On general question, so how do you classify neighborhood of leaves out of, well, the leaf is transversal and whatever maps. Even for a circle, I know. A torus, I don't know. A sphere, I know. A torus, I don't know. Thank you.
Hey, thank you very much for this beautiful course, but we still have time for questions or comments. Chen Chang.
So at the moment when you were constructing this holonomy groupoid, right?
Mm-hmm.
So you have this atlas, disjoint union of A spiral, these guys.
Yes.
And then you model out the equivalent relation. That was some sort of equivalence relation between bisections, right?
Yes.
So this Z is also bisection between X and Y. Was it like in that? And I just want to ask you, like, the equivalence relation you want to model out, do they also form a nice space?
Well, I see what you I think you want to, I see. Well, first, when you have a bisection here, you can lift it to a bisection here. When you have a bisection here, it goes down to a bisection here. This works. So in some sense, you have one correspondence between bisections of x, z, and y. No, I totally agree with you that z, in fact, it's a bisubmersion between x and y.
Right.
So it's a bisubmersion on the top of a bisubmersion.
Right.
Probably the beginning of an infinity groupoid.
Well, the first step to check is whether Z they form a nice space, because your atlas is a very nice space. Right?
Okay.
The thing before you model out is a B object, right?
I'm going to explain to you. When I have bisubmersion, there is a singular foliation which is K of Ts inter K of Tt. So taking the sum, I take the intersection. And these equivalences, as soon as I become between x and itself, it's a bisubmersion for this singular of a foliation. You see? And it is again in Ruben-Lewis article. You see? Take K of Ts, K of Tt intersection. It's a singular foliation, and these equivalences are bisubmersion. So you have bisubmersions, bisubmersions on bisubmersion, bisubmersions on bisubmersions. I think it's the beginning of an infinity groupoid.
It sounds very good. Thank you. Thank you. Yeah, I have a question about these projective resolutions of singular foliations. So, in how far is this constructive? So, if I give you a singular foliation, is there a recipe for making such a resolution? And also, is there a recipe for telling how long the resolution has to be at minimum?
So, for how long the resolution has to be, the Syzygy theorem says you that if the dimension of the ambient manifold is n, you have one of length minus 1 n plus 1. So yes, in fact, at an arbitrary, if you look at the neighborhood of an arbitrary point in the real analytic holomorphic or algebraic case, the length of the resolution is less than the codimension of the leaf plus 1. That's Syzygy theorem. Well, so you are asking how much of this Syzygy is constructive. I'm really not very competent for this question, but I think there are even softwares that compute them.
Okay, thank you.
So I would say yes. Leonid Rifkin is not here to help me, so I think.
So your favorite example, the vector fields on the plane vanishing quadratically, can you compute it?
Yes. Yes, because in that case, it's just all vector fields times some ideal. So I just have to take the ideal of resolution vanishing quadratically at 0, which has 3 generators and 2 3 generators and 2 relation, which is y times this is x times this, y times this is x times this. So the resolution has length 2 and is given by this. In general, if I take vector fields vanishing on something, I just take the ideal of functions vanishing on something, take a causality resolution, for instance, it will give a resolution of vector fields.
It's still hard to find if it's homotopy equivalent to an algebroid, since you can compute it so explicitly.
At least I don't know how to do it, yeah.
Okay, any more questions? Alphonse, you're trying to make your point from the end of the
My question is also related to constructions of the L-infinity algebroid.
Yes.
When there is a finite amount of generators for the foliation of manifold, I mean, not only that, but also the generators being analytic, then I believe it's possible. But what happens if the amount of generators is infinite? Like in a point
Okay.
you have analytic generators, and
Okay.
another point you have more, and so on.
So what I haven't said, that in some sense, this result has nothing to do with singular foliation. It has to do with Lie-Reinhardt algebra. And in fact, with Ruben Louis, it's the first part of his thesis, he proved that for any Lie-Reinhardt algebra, any projective resolution might be infinite dimensional, horribly dimensional at each set, the linearity algebroid exists. So in some sense, it has nothing to do with any of that. Like you can even define it for any partition manifold. Like A vector fields tangent to it, it's a Lie-Reinhardt algebra. Take any resolution, it works. But when it's not when it's not a finite dimension, we don't know what to do with that. Right? Then you can always choose a Lie algebra. It takes a free Lie algebra with R generators. Okay, done.
Okay, any other questions? In the room, online? No, so let's thank Camille once more.